Good morning. Welcome to NGSS Physics. So we are going to be talking about density today. And if you want to think about something when you're thinking about density, think about compactness, because that's what density is all about. This is a concept that started a long, long time ago, before Isaac Newton and most of the scientists that we've already been talking about. Basically, these naturalists figured out that there is a relationship between the mass of a substance, or the amount of matter of a substance, and the amount of space that it takes up. They called that ratio of mass to volume, they called it density. And today we can quantify the density by taking the measurement of mass and dividing it by the measurement of the volume. You can use this formula right here. It's a very basic formula. Notice that there are three variables in the formula, so we could, instead of solving for density, solve for volume instead, which would be the mass divided by the density, or the mass, which would be the density times the volume. And what I've drawn down there is a density triangle, so that if you have trouble manipulating formulas, you can just stick it in there, and you can solve for any of those variables. Or you could just write down the formula all three ways. What is the volume in the density equation? Well, this is a three-dimensional quantity. It's the amount of space something takes up. And because it's three-dimensional, the units are going to be a cube value, like centimeters cube, which is the actual units that we're going to use for density. How do you calculate the volume? Well, if it's a nice geometric shape, like a cylinder or a cube or a rectangle, you can use a geometric formula. For instance, length times width times height for a cube. If it's a liquid, something like that, then you would have to use some kind of a measuring device. For density, we are going to use the units centimeters cubed. Another variation of that unit is the milliliter. And the milliliter is really just a centimeters cubed. We just use a measuring device to get there. And so it's a derived measurement. Let me show you. Here is a graduated cylinder, which uses the cylinder formula. And by using that cylinder formula, somebody put graduation marks on this tube. And if you pour a liquid in it, you can actually measure the actual volume. It's tricky though. You have to make sure that you're measuring the liquid at the meniscus, which is the curve of the liquid. And you need to make sure that your eye is level with the meniscus. Otherwise, you might get a faulty volume reading on your graduated cylinder. And you don't really want that. Okay? What if we have a solid object and you want to measure the density and you need to measure the volume part of the density? How do you do that? Well, we could do this thing called water displacement. This was discovered right about the time that density was being discovered by Archimedes. And he basically figured out that an irregularly shaped object, you can't find the volume by doing water displacement. What you would do is you would first take a graduated cylinder and put a known amount of liquid in it, okay? And when you put that known amount of liquid in it, go ahead and read what the volume is. So let's pretend like the volume is, okay, right there at this mark right there. And then you would add an irregularly shaped object to your graduated cylinder, and hopefully it'll sink below the water level. And when it does, the water level will rise up higher. Well, the amount that water level rises is the volume of that irregularly shaped object. All you need to do now is read the volume before and after and do a simple subtraction problem. The mass is the second part of the density formula, and the mass is actually a measurement of the matter an object has, and we measure that mass by measuring basically that against the gravitational pull of the Earth, and we use a balance to do that. And for density, unlike most of the physics formulas, the unit that we're going to use for mass is going to be the gram. All right, let's take a look at some practice problems here. Practice problem number 1, calculate the density of a 10-gram cube of wood with sides 5 centimeters long. So I need my density formula, which is the mass over the volume. And I see that here is my mass, which is 10 grams. I'm going to divide it by my volume, which they don't give me. But they do give me all the sides of the cube. And I know that the volume of a cube is length times width times height. And I get 125. And since they're in centimeters, I've got centimeters cubed. So down here, I'm going to have 125 centimeters cubed. Okay? And I'm going to get an answer in grams per centimeter cubed, and I believe the answer is 0.08. I know there's a lot of little lines showing up. Can't help that. Determine the mass of a sample of metal if it has a density of 7.5 grams per centimeter cubed and a volume of 5 centimeters cubed. Now remember that formula at the beginning, if you wrote down the 3 different versions of it, then you figured out that mass is actually equal to the density times the volume. Okay, just basically times by volume on each side, and you get the formula solved for mass. So here's my density, 7.5. Here is my volume, 5. And I plug those numbers in, and I get an answer very, very close to 37.5. Number 3, the volume of a liquid. So if we're going to find the volume based on our formula, the volume is actually the mass divided by the density. Okay, and here is my mass, it's in grams, and here is my density that goes down at the bottom. Plug those numbers in, and you get somewhere close to 16.7 milliliters. Now let's take a look at this one. This is a little bit more challenging. Find the density, and I need both mass and I need both volume to do this. Here I get some grams. I can see that, oh, that's my mass. It goes in up there. But it doesn't tell me the volume because it's an irregularly shaped object. But I can see that my liquid started at 50 and ended at 75. So if I do a slight subtraction problem, I get a difference of 25 milliliters. That is the volume, and it goes in right there. So my answer is going to be a little bit less than 1, 0.94 grams per milliliter. All right, so, I told you, if you think about anything, think about the compactness. So what's really going on here? The molecules are moving around constantly. We call that movement of molecules kinetic energy. And sometimes the molecules are moving very, very fast. And if they are moving fast, they're hitting each other and they're bouncing off, and they've got a lot of space between them. And that's what we call a gas. Sometimes molecules aren't moving very fast. They're just kind of vibrating in space, and they get very close together. And we usually call that a solid. And somewhere in between, we have things in the liquid state. Well, when things are very close together, that means that their volume is small. So if you think about that formula, density is equal to mass over volume. We'll pretend like all 3 of these samples have the same exact mass. If that mass is small, then the calculation is going to give us a big number for density. So the smaller the volume, the bigger the density number. On the other hand, over here for my gas, the volume number is very big. So if that number on the bottom is bigger, then the density is smaller. So for gases, have a very small density compared to a solid. Which tells us that, there are going to be some factors that affect the density of objects on Earth. And temperature is one of the main factors, because temperature really will affect the volume of something. Okay, and the volume is down here on the bottom. And remember, as the volume increases, the density will decrease. As the volume decreases, the density will increase. So volume changes directly with the change in temperature. Think about a balloon. As a hot day approaches and you've got your little balloon, it swells up, so happy, and it gets to be a bigger volume. On the opposing side, on a cold day, the volume of your balloon will probably shrink down and get a lot smaller. So increases in temperature result in increases of volume. And if that volume increases, then that means the density will decrease. So increases in temperature result in increases in volume, and the density drops. It's exactly the opposite if the temperature decreases. Then the density will rise. Pressure also affects the volume. Okay? If you put pressure on your balloon, you start squeezing your balloon down, what happens to the volume? It gets smaller. So volume changes inversely with pressure. As you squeeze in, increase the pressure, okay, the volume will decrease. It'll get smaller. So those are opposites. Okay, and remember, it's not pressure in the formula, it's volume. So as the volume changes, the density changes. Increases in pressure result in a decrease in volume, and so therefore the density increases. Okay, as you increase the pressure, the volume decreases, the density increases. If you decrease the pressure, the volume will expand and the density will drop. So it'll be the exact opposite. All right, so let's talk about density difference in the early Earth. The early Earth was made up of fluids, lots of liquids and gases, and because they had different densities, and the density was in direct relation to the amount of mass the substances had, they layered themselves according to density. These substances that had more mass, okay, was more attracted to the center of the Earth, and they sank. And so Earth actually layered itself, okay, through density layers. The more dense substances sank, the least dense substances rose to the surface, very similar to being in a pool. If you had something that was very dense, denser than water, it would sink straight to the bottom. Something that was not so dense, not as dense as water, would float right on top. And so the early Earth, being made of lots of different density substances, those objects were able to layer themselves according to their density. This is still happening on Earth today. In fact, all of the weather, all of the ocean currents, okay, things that are happening in the deep solid parts of the Earth are all being affected by density differences. For instance, convection currents in the water, warm air where the molecules are moving faster, the volume expands and that warm water rises to the surface. On the flip side, cold water, the molecules are not moving as fast and they stick together and cold water sinks. This creates density currents in the ocean. So that's one place that we see density differences. Atmospheric. Over here, I've got warm air rising, and it does. As asphalt over air heats up the air, you probably saw that rising waves of air going up into the sky. And warm air rises, whereas cool air sinks. Think about a hot air balloon and how it rises up. This creates a cyclic pattern in our atmosphere, and it's what causes the wind as air is rising and sinking. In the deep Earth itself, tectonic geology are driven by convection currents. Warm areas inside the Earth, like here, we have this thing called upwelling, where the magma rises to the surface, and it could be solid or semi-solid. And then cooler areas where it sinks, creating convection currents that get everything moving around due to the changes in density. One other thing about density is the buoyancy force. We talked about forces in the last chapter. Well, there is a buoyancy force, which is affected by the density of the fluid an object is submerged in. When the buoyancy force is exactly equal to the force of gravity, an object will float. Don't worry about this formula. We're never going to use it in a calculation, okay? So don't worry too much about it. I just wanted to make sure I pointed out the buoyancy force to you. All right. So in summary, density is the ratio of mass per unit volume. Temperature and pressure can affect the density of substances. Changes in density create all of the things around the Earth, like convection currents in the atmosphere, the deep Earth, and in the ocean. And the buoyancy force, okay, partly depends on the density of the object. Thanks for listening. I will see you guys a little bit later.